Thank you. I'm Hiroki Usuba and a PhD student at Meiji University from Japan. We will talk about modeling lassoing motions considering the criteria. In graphical user interfaces, there are many methods for selecting multiple objects. For example, there are rectangle selection, tapping, and lasso selection. Users use the rectangle selection when objects they would like to select are arranged on a regular layout. In the rectangle selection, by drawing a diagonal line of the object, they can select the object. When selecting objects arranged on an irregular layout, users also use tapping in combination with the rectangle selection. The users use the rectangle selection and then select the remaining object by tapping. Another option is lasso selection. In the lasso selection, the stroke drawn by users is the selection range, so the users use the select object by enclosing the object. Especially for the lasso selection, there are many criteria depending on applications. So even if users draw the same stroke, depending on the criteria, the selected objects are different. Suppose users would like to select only the 5 center yellow objects. First criterion is called center in this study. The center criterion selects objects whose center are within the selection range and succeeded in selecting only the yellow objects. This criterion imitates cycling selections. Second criterion is called part. The part criterion selects objects that are partially within the selection range. In short, when users only slightly touch objects, the objects are selected. So, even in drawing the same stroke as that of the center criterion, some objects are incorrectly selected. This criterion is implemented in Adobe Illustrator. Last criterion is wall. The wall criterion selects objects that are completely within the selection range. Also in the wall criterion, the selection is failed. One yellow object is out of the selection range. This criterion is implemented in Microsoft OneNote. In this way, even in drawing the same stroke, the selected objects are different. If users would like to succeed in selecting the objects by each criterion, they should draw the stroke like that of this slide. The shortest stroke is that of the path criterion, and when visualizing the path width users can steer through on each criterion, it becomes a green arrow. The path width is shifted by each criterion, but the length is always the same. Here, we introduce a model for predicting the movement time of path stroke. The model is called steering law. Simply speaking, the steering law shows the movement time depends on the path amplitude and width. So, based on the steering law, because only the path amplitude on each criterion changes, the predicted movement time for path criterion may be shortest. In actual GUIs, there are many lassoing criteria, but its features are unclear, and a model considering the criteria does not exist. So, in this study, we conduct 2 experiments, straight line path and Oneloop path tasks. In the straight line path task, because the path amplitude is fixed for each criterion, we believe to find the pure effects of the criteria on lassoing operations. And because the lassoing operations consist of the steering through a straight line path and turning at a corner. By conducting the task, we believe to build a baseline model for the lassoing operations. In previous studies, Yamanaka conducted steering through successive objects and lassoing in a grid of icons, and they succeeded in modeling the operations. However, in their tasks, users could not touch any objects, so their task did not consider lassoing criteria. If conducting the criteria, users can partially touch the objects. In short, the lassoing performance considering the criteria is unclear, and the model considering it does not exist. In the experiment 1, to pass amplitude 4 vertical intervals, whole object size, and 1 horizontal interval exists. The horizontal interval was 10 pixels, so with it the participant performed visually controlled steering motions. The participant conducted the task by each criterion. In the task, the selection range is created by combining the participant's stroke and endpoints at the bottom of the screen. This is the center criterion part. And whoa. The participant trajectories shifted depending on the criteria because the tolerance width also shifted depending on the criteria. For example, in the center criterion, the participant draws stroke in the middle between the objects. So the participants could correctly understand the difference between the criteria. For the performance results, there are no significant differences in the criteria. On the other hand, the movement time were affected by the other factors. The steering law can be expressed as the slide for all criteria. The model showed good fits for all criteria, so the straight line path task could be modeled for all criteria. Next, we conducted the one loop path task. 3 criteria, 3 object size, 3 intervals, and 3 numbers of target row and columns existed. When NRC is 3, the targets lined up in a 3 times 3 grids. The red part of the stroke was handled as a selection range. This is the center criterion. Part and 4. Also in the experiment 2, the participant trajectory shifted depending on the criteria. For example, when using the center criterion, the participant drew the stroke in the middle between the objects. So, also in the experiment 2, the participant could correctly understand the difference between the criteria. Although the path amplitude changed for each criterion, there are no significant differences between the criteria. On the other hand, the movement time was affected by the other factors. The effects of the other factors were consistent with the steering law. For example, for the center criterion, the steering law can be expressed as a slide. By doing the same way for all criteria, the steering law showed good fits. So, the one loop path task could be modeled. According to Pastel's story, canonical tasks show better fits by adding fit time. Our one-loop task also included canonical operations, so we verified the model fitness by adding fit time. For example, in the center criterion, the term can be expressed as a slide. However, considering ARC value, fit time did not significantly improve the model fitness. We set 30 checkpoints for analyzing the average speed. According to past story, canonical tasks require the stopping motion. However, in our task, the participants smoothly repeat the acceleration and decelerations. Therefore, we believe fit time did not significantly improve the model fitness. In short, the steering law is sufficient to predict the movement time of the Oneloop task. As at experiment 2, we asked the participants how easy the operation was for each criterion on a 5-step recursive scale. The Freedman test showed the difference between the criteria was not significant. So, for the subjective evaluation and performance, the difference between the criteria was not significant. We conducted the straight line path and Oneloop task. By 2 experiments, we found the difference between 3 lassoing criteria are not significant. The lassoing motions concerning the criteria are affected by the steering factors, and the steering law falls for 3 criteria. There are some limitations in this theory. In large-scale displays, lassoing operations have longer path amplitudes. And in a 2x2 grids, when using the center or path criterion, users can draw a sharper stroke. In this study, when conducted, there were no significant differences between the criteria, but in such conditions, there may be the difference of the movement time for the criteria. And we would like to compare with other criteria. For example, selecting objects whose 80% area is in a selection range. After comparing with such criteria, we will build a modeling including criteria as a variable because such a model is more convenient. Again, this slide is a summary of our story. Thank you for listening.
Thank you. Questions? So it seems everyone understands everything. Okay. So, yeah, of course, the first question comes as an application. So, so when you are talking about the modeling, I mean the criterion in some other context. So, do you have any plan to record the users? More movement. So lassoing movement on some other application like games, and try to see that model those. The time or error in that way. So, is there any of your next plan?
Yes, thank you for comment. Your question is for more complex conditions modeling. In previous studies showed in previous study conducted more complex layers not considering the criteria. So if we use their model and combination with our results and more complex layers could be modeled, we believe.
Yeah, so I'm thinking of kind of task, like start and end. So you need to define through a path. You need to find a path through some objects. And there are multiple paths, but you need to have some kind of particular shapes, and you move in that kind of. So your lassoing might be more control if you have some kind of a game or some kind of application where you need to find from A to B. You need to find a path, and the path is not straight. There are some objects, some obstacles, or there are some dead end of the road. So you need to move like this way, and so those kind of movements could be modeled by this kind of. So I can understand that any kind of shapes could be modeled. Lassoing, right? So those kind of shapes or those kind of applications could be could be tested as a model fit or not.
So, sorry, one more.
Okay. So I mean, some different kind of. So if you think about the smaller games, that people say that, okay, you have point A and point B. So you can think about a garden. You have a point A and the point B. So from one door to another door, and then you need to find a way through the garden. And there are some blockage doors in between, so you need to find the movement in that way. So you are having zigzag movement, or you are having some kind of unshaped movement, not that straight movement. So might be this kind of criteria would be, useful for, modeling the time, how much time you take, and also the speed, how you actually can move. So such kind of application could be. Okay. So yeah, we can talk about later.
Sorry.
Yeah. No problem. Any question? Oh, yeah, please.
Hello, I'm Laurent Théverin from LMU Munich. My question was, I think the difference between these lasso selection modes are interesting when some object overlaps. So do you think when you have if you have to do such task when squares that overlap, you have to decide if you have to take like all the object or the both object of only one object? It could change the equation or something.
You can suggest when objects overlapped. So for special criteria, they did not select for one path stroke. So if for such condition, it is difficult for modeling and testing it. Okay.
Okay. Thanks once again to the speaker. Yeah. Thanks.